Okay? All right. All right, so wow, okay, so we're going to take some time, and we're definitely not going to get to the new section, but we had some stuff left on this example. So we're going to take the next like 10 minutes or so, finish it, and then we'll spend class time that you'll be able to use to work on the assignment and ask questions. I'm going to float around the room here to look at stuff. I'm going to keep my eye on the chat window if folks want to ask questions. This is really frustrating for folks in Wilson today. I apologize for that. We just found, last class we found the function that tells us like how many grams of salt are in the solution. Oh, Peter says we good. All right, awesome. So that we found this function that gives us the grams, the amount of salt in grams in the tank at time t. Let's go up and see what they were asking us about. We want to get to 1 gram per milliliter, or 1 gram per liter, rather. And we want to know, will the salt concentration reach the desired level before the container overflows? Because the input rate was at 2.5 liters per minute, and the outflow is just 2 liters per minute. So the overall volume is increasing at 0.5 liter per minute over time. And that was, we got this nice volume function. So if we want the concentration at 1 gram per liter, and I'm going to use some, magic paper here. So we want the concentration to be 1 gram per liter, so that means we want 1 to be equal to x of t over v of t. And in the example before, the volume was constant, so it was simple as just finding how much salt, right? Like setting the salt at the right level. But now both of these are functions that change over time. So our x of t function over the volume, which is 150 plus 1/2 t, right? Yeah. And this 150 plus 1/2 t, that's like, I've got fractions within fractions, so I'm going to kind of just pull this out as a separate fraction. I'm going to multiply the top and the bottom of that fraction by 2 to clear the denominator. So I got 2 over 300 plus t times x of t. And this is what we want set equal to 1. We found that x of t function. That's what we finished off on last class. And I'm going to scroll up just a minute to, okay, times this function here in the black box. So okay. Now we're just going to solve this equation. I'm going to start, I think, just by distributing this fraction, because the 300 plus t will cancel nicely. And then, of course, we'll have that factor of 2 to distribute on top. So when we distribute this to the first term, we'll get just 3. And when we distribute it to the second term, 2 times 430 is 860. Times 300 to the 4th over. And then we're going to increase that power on the bottom by 1 because it's the same base, 300 plus t. Like so. We can subtract 3 from both sides. And then I'm just going to get rid of the negatives. I think we can multiply both sides by 300 plus t to the fifth over 2. That'll give us 300 plus t to the fifth. That is equal to 860 times 300 to the fourth power over 2, or 430. Now it's not too bad. We're just going to take, what, the fifth root and subtract 300. Minus 300. 430 times 300 to the fourth, all to the 1/5 power, minus 300. We get 22.4 minutes. So this is how long it will take for that concentration to get to 1 gram per liter. And the question they asked was, will it reach the desired concentration before it overflows? So I think the only thing left to do is to find what the volume is at this time and compare it to the capacity of the tank. So and that was 150 plus 1/2 t, 1/2 times 22.4. $161.2 liters. What does that mean?
Max is 160.
Oh, right, yeah, so they told us the tank was 160 liters, so it'll overflow before it gets to the concentration. There's a problem on the assignment that you're going to turn in on Friday that is kind of similar to this. Only I think instead of increasing the input and wondering if it'll get to the desired concentration before it overflows, we are increasing, let me see how it's worded.
Increase the concentration of salts.
Let's see. We're reducing the input flow to 2.5 liters, and it's flowing out at 3 liters per minute. So, in fact, over time, the volume is like decreasing a little bit. And so, the question that you're going to try to answer is, will the tank reach the desired concentration before the tank empties? Right? If the overall the volume is kind of decreasing over time. See if we reach our goal before it empties out. That problem. So there's number 5 and number 6 are similar to this example and the one before it. So the first one that we did, That's this one. So this one is sort of like, you could refer to this one for problem number 5. And that one is a bit more doable because the volume isn't changing over time. And then number 6 is kind of like 214, the one that we just finished. Takes a bit more work to figure out. Are there questions that folks want to ask? I'm going to give it a minute because I know that folks in Williston will probably have to probably type their question in via chat. Okay. All right. What we'll do then is take, we kind of lost some time at the beginning, but we'll go ahead and take the rest of the time so that you can work on the assignment. We'll finish this, we'll do the next section on Wednesday. And I'm hoping we'll get to take full advantage of the beginning of class time to get all the way through that. There are practice exercises that we'll have for that section, but they'll be posted to Canvas. In fact, they're actually already posted to Canvas because I posted it under today. But we'll do this next time. So I'm going to be here obviously I am here in Randolph, covering questions that folks have. On Wednesday, I will be in Williston. We'll do something similar, and I'll be there to answer questions in the room in Williston. I'm going to keep Zoom open and keep an eye on the chat window in case folks have questions they want to pose in Zoom.